Um, so a few of you have replied to the survey asking when we might do some review and go over some of the homework exercises we haven't had the opportunity to yet. Most people that have responded so far have said 6 p.m. would be the best time, which is fine with me. But if, for whatever reason, you can't make that time, just send me a message and we can talk some other time later in the evening or perhaps Wednesday before the exam. Just let me know. So that it's looking like 6, but of course the survey's still open. So if much more of the class has a very different opinion, then we can change the schedule. Nothing is set in stone. Okay, so I hope you all had the opportunity to watch the lecture from Friday. And if so, you'll recall that we proved a couple of really nice theorems about conjugation, right? Namely, for an arbitrary isometry, alpha, we described what it means algebraically and geometrically, what it means to conjugate a translation and a rotation by an arbitrary isometry alpha. Okay, so there's just a couple related results that we can now address about which isometries commute with one another. And that will basically wrap up chapter 7. Oh no, sorry, and then we'll talk about dihedral groups. Okay, so first of all, we have the following theorem, which characterizes when reflections commute with one another. Okay, so we have sigma n is equal to sigma n, sigma m, if and only if either m equals n, in which case, of course, we have the identity on both sides, or m and n are perpendicular. So, let's see why this is. So, this equation holds if and only if we were to have m conjugated, sigma m conjugated by sigma n is equal to sigma m, right? We've just multiplied both sides by sigma n on the left. Okay, so in other words, what does this mean? This is the case. Well, now we use our formula for conjugation, right? This would mean that sigma sub sigma n of m is equal to sigma m, right? Which of course is the same as saying that sigma n of m has to be m, right? I mean, symbolically what I'm doing is just equating the subscripts, right? This is
that relies on the fact that reflection is unique, right?
That a reflection is unique. It's determined by the line about which you reflect. Exactly. Okay, so now, from our study of the basic properties of reflection, we know that either n is equal to m or n and m are perpendicular, because that's the only way sigma n fixes a line, right? So this implies our result. Okay, good. Now, let me ask you, under what conditions do rotations commute? What do we think about that?
The same center.
Okay, right, we've seen that result before, right? Rotations of the same center always commute. Is there any other conditions under which rotations commute? What does your intuition say?
No.
No, that's the correct answer. Those are the only conditions under which rotations commute. Yeah. Right. A bit of a trick question there. Right, okay, so non-identity rotations with different centers do not commute. Okay, so let's see the formal justification of this. So let's take a conjugation, rho sub d comma phi times rho sub c comma theta times rho sub d comma phi inverse, which by our formula for conjugation is just rho sub d of phi of c comma theta right, okay, these rotations commute if and only if we have
Rho sub d phi fixes c.
say that one more time.
Rho sub d comma phi fixes c.
Right, we're going to do the same type of thing where we equate the subscripts, right? Okay, so what we have is rho sub d comma phi, rho sub c comma theta, rho sub d comma phi inverse is equal to rho sub c comma theta, rho sub d comma phi, rho sub d comma phi inverse, right? So I'm taking the left-hand side of this and just saying if they commute, then I'm able to switch the order, right? So in other words, this implies that I would have to have, well, first of all, let me just write, obviously, this means that this conjugation is just rho sub c comma theta, okay? So if they were to commute, I would have to have rho sub d comma phi of c comma theta equal to rho sub c comma theta, right? This is by the formula for conjugation that we have, and this is assuming that they commute.
That doesn't cover all the cases, does it?
What cases, Mitch?
Switching those two specifically isn't a generic solution, right? It would just show up with the other switch.
I'm sorry, say that one more time.
If you switching the first two terms could theoretically be possible without, like, give you a correct answer without, but the second two terms might not.
No, I think this covers all the cases, right? Because like even if I switch the other way, I still have the identity on the other side, right? So yeah, it's immaterial which way I chose to commute these. Right, so I guess what a better way to say that is we're going by contradiction, right? So taking any consequence of that and showing that it produces a false result. Okay, good question. Okay, so in other words, this is to say that rho sub d comma phi of c is equal to c. But remember, the only fixed point of a rotation is its center. So this is the case if and only if d is equal to c. Contradicting that our rotations had different centers. Okay? When I entered the building today, I was excited because it seemed like they finally turned on the air conditioner. But rest assured, people on Zoom, it's exactly as hot in this room as it was last week. So, sorry for the glistening. Okay. So, what can we say about the product of two non-identity rotations about different centers? Well, there's sorry. Yeah.
Which means they're still going to be even. Which means you'll have a rotation or a translation.
Yeah, good. So in fact, it works out as nicely as you would expect when you take the product of two non-identity rotations with different centers. Their angles add. Okay, so let's see why that is, and maybe say a little more. Aptly named the angle addition theorem. Okay, this has several parts. A rotation of theta degrees followed by a rotation of phi degrees is a rotation of theta plus phi degrees unless theta plus phi degrees is equal to 0 degrees. And when I say equal, of course, I mean up to a multiple of 360. Right? This is equality of degrees is this kind of modular thing. Right, yeah. Okay? So what happens in the case when theta plus phi degrees is equal to 0 degrees? In which case, the product is a translation. Okay. Secondly, a translation followed by a non-identity rotation of theta degrees is just again a rotation of theta degrees. That kind of makes intuitive sense, right? If you rotate let's say you slide and then rotate, it's still a rotation of the same amount of degrees. Okay? And thirdly, if you do this in the opposite order, it's also still a rotation of theta degrees, right? A non-identity rotation of theta degrees followed by a translation is a rotation of theta degrees.
So you're saying that even if we like rotate something and translate it, it's not considered a translation and rotation, it's just considered a rotation?
That's what we'll show, that in fact,
But a different center.
of a different center, exactly. That's right,
Okay.
Ryan. Yeah, so when you translate then rotate, or rotate then translate, it's a rotation about a different center.
So all we have to do to prove that is be able to have a system that finds the center here.
Yeah, right, that's what the proof will consist of. Explicitly how to find the center of this new rotation. Good. Right, you know, this is a good point, right? It makes perfect intuitive sense that this is true. But I'm glad you say this, that's exactly what the proof consists of, demonstrating what the center is of that new rotation. Okay, so let's start with one. Okay, so let's consider the product rho sub b comma phi times rho sub a comma theta. With a not equal to b. And let's set the line C to be the line through the centers of our rotation. Okay? And we also know there is a line A through point A and a line B through point B so that we can express both our rotations as a product of reflections, right? Namely, we'll take this line C and we find the line A that has a directed angle measure theta divided by 2 from C.
From this picture before.
Yeah, yep, that's right. And if you remember that picture, then you'll see why this case happens. Okay, so we're gonna redraw that in case we didn't really have that conversation out loud all the way, but that's what we're doing. Okay, so in any case, second rotation as, okay, so notice, so I found the A so that I'm changing the order of the angle measure that I take for both of them, right? So you can probably imagine that's because I'm going to do some kind of like out-rake maneuvers, and this is helpful to do it this way. Okay? So, now if I look at my product, rho sub b comma phi, rho sub a comma theta, b phi, rho sub a comma theta is just equal to sigma b, sigma c, sigma c, sigma a, which is just sigma b, sigma a, right? So now let's address the case where theta plus phi is 0 degrees. When theta plus phi degrees is equal to 0 degrees, the lines A and B are parallel. Okay? So the product must be a translation, right? This is from our characterization before of translations, right? All translations can be written as a product of reflections in parallel lines.
And by that is twice the direction distance.
Right.
So it's like the same, we're not trying to get fixed points this time.
Say again?
It's like the same, but it's not fixed points this time.
Right. Right. Same exact picture. And so let's draw the picture. Right. So here's all the information. Sorry, I should put this a little lower. Here's all the information that we've said so far. Here's our line C. Here's our line A. And here's our line B. Okay? And here I have theta over 2. And here I have phi over 2. Okay? So how did I deduce this? Well, how did I deduce that they must be parallel? Well, add these together and multiply by 2. You get 360. Right? That's the only way you can get a multiple of 360 for theta plus phi degrees. Okay? So, otherwise, if we have theta plus phi degrees not equal to 0 degrees, then the lines A and B intersect somewhere, right? At some point, call it C. Okay, so let's draw this scenario as well. Okay, I have my line C, I have my line A, and my line B. here's my point, capital C. Right, I have my points A and B here. Just for completeness, I forgot to write that here, but of course, A is where line A intersects C, and B is where line B intersects C. Okay, so again, this angle, this directed angle is theta over 2. And this angle here is phi over 2. Okay, and then remember, either use a triangle and subtract 180, or remember the exterior angle theorem, same thing. This is phi over 2 plus, I'm sorry, theta over 2 plus phi over 2. Okay, so in other words, what this implies is that we have our new center is C. Okay?
And we can show it's a rotation just because it's, we know it's part of four functions.
Yeah, that's right.
And not transition.
Right, the only way it can be a translation is if you have this scenario where they're parallel. Okay, so altogether, what this shows is that our product, sigma B, sigma A, is equal to the rotation centered at C of theta plus phi. Sorry, comma phi, theta plus phi. Okay, i.e. twice this directed angle measure. Okay. So, what about a product of a translation and a rotation? Well, of course, here I mean a non-identity, right? Well, and notice I said parts 2 and 3 separately, but it actually, we can address them both at the same time. Okay, so what we do is just write the translation as a product of half turns. Remember, that was the first factorization theorem that we did. That we could come up with a pair of points such that any translation can be written as the product of half turns around those points. Okay? So, then, a translation times a rotation as a product of 3 rotations, right?
Which we can simplify like we just did down to 1.
Exactly. It's the same. Now we're back in case 1, right? Because we're just dealing with the product of rotations. Okay? So, and it's a particularly easy case because we know that half turns both are rotations of 180 degrees, 2 of which are 180 degrees. So, in other words, by the angle addition theorem, we have that this rotation, this isometry, that's the product of translation and rotation, is theta plus 180 plus 180 degrees, which is just theta degrees. Okay, I should say by part 1. said, we had to identify a new center. But then, actually, it's just angle arithmetic that shows that you can take a translation and a rotation in either order, and you still get a rotation by 180 degrees. Of course, I'm sorry, by theta. Of course, I didn't explicitly construct the center, but it's just the same procedure that we did in one. Okay? Okay.
So how does that work if they're parallel? There's three of them. Or do two at a time? Doing construction.
Sorry, say that again?
When you're doing construction for that case, do you have to do two at a time?
Let's see. Yeah, right. You do two at a time, but in any order you do it. In any, that is to say, it's associative. You can do either pair first, and then do the result of that with the third one.
Well, how would you do the one? You can't do the 180 together, can you?
Say again?
You can't do the 180 together, can you? Then you can't put the translation with the rotation.
Oh, that's a good point. You're right. You do have to do theta 180 and then the other 180. Good. Yeah, I didn't think of that before, so that's good. Thank you for bringing that up. Okay. Good. So this completes our classification of even isometries, right? We know everything that we can say about even isometries now. Of course, there's always more to say, but so now what we'll do is talk about, we'll go back to studying symmetry groups of certain figures of geometrical interest. Okay? Namely, we'll talk about the dihedral groups. Okay, so we spent some time earlier in the summer trying to describe the symmetry groups of rectangles, right? And I think we also did an exercise, we did a homework exercise where we talked about all the possible symmetry groups of triangles. Right? A triangle has symmetry group of order 1, 2, or 6. Right? We did that.
That was homework exercise, yeah.
Yeah, I think we did that, and then we talked about it in class together after everybody did it at home. So now, we'll determine the symmetry group of a regular n-gon. Okay? For n greater than 2. Obviously, there's no bigon in the plane. Okay, so start. Let's consider a square. Oriented in the plane as follows. Okay, so oh, that's terrible. It's really not good. going so badly. Go way off the mark. I'll start at the center. Let me put some labels on this. So we have, we'll call this axis H, of course, usually the x-axis, but just to make consistent with our notation that we use for the Klein Four group. V, likewise, I'll call this line R and this line L. And I'll also label these two vertices, V1 and V2. Okay, so if you remember our study of the symmetry groups of the rectangle, we always had the caveat that the rectangle was not a square. Right? And I made some offhand remark about, it's like, well, a square has more symmetries, right? It has rotational symmetry, not only reflectional symmetry. So let's make that precise now. Now that we've studied rotations quite a bit more, we can actually put some concrete computational devices behind that. Okay? So let's say square is fixed by, for shorthand, we'll write rho, but what I mean is, of course, here is our origin, O. We'll write shorthand rho for the rotation centered at the origin by 90 degrees. And sigma, shorthand for our old friend from the Klein Four group, sigma h. Okay, of course it's fixed by more than that, but bear with me. Let's see where we can get with just these two. Okay? So, note the relation rho squared is equal to sigma, right? That is to say, if I rotate this square by 180 degrees, that's the same thing as reflection about h. Okay? Which, of course, implies we know sigma being a involution. This implies that rho to the fourth is equal to sigma squared is equal to iota. Okay? So, right. Since we proved the symmetries of any figure form a group, we know that rho squared, rho cubed, and rho to the fourth, obviously equal to iota, all fix the square. So, I mean, why am I saying this? You can see this, obviously, but I'm just trying to kind of build up the entire group. Yes?
So you have sigma equals sigma h?
Yeah. Yeah. Is it?
Sure, rho
Oh.
squared equals sigma, then?
I feel like it has to be about number, it's a point reflection, it's a half turn, right?
No, sigma h is a reflection about h, right?
That was two rotations equivalent to that reflection.
Okay, so let's see. Two rotations puts vertex 1 here, right?
Right, which is.
Yeah. Okay, where did I make a mistake here?
needs a half turn.
Hmm.
Or sigma could be the product of sigma H and sigma B.
What have I done here? What did I do wrong? Huh. Okay, so let's see. Hmm. What did I go wrong here? Okay, so yes. Yeah, I guess you must be right. It has to be the half turn. Right?
Don't we define dihedral groups to be generated by a rotation of reflection?
Yeah, that's why I'm confused here. And you know, I didn't, and this is my fault. This is exactly what it says in the book. And I was like, oh yeah, that makes sense without actually checking. So let's see here. Oh, you know what? I think I realized my mistake now. This is blatantly false, what I wrote here. We should take this to be H, and not this. We can deduce this without that intermediary step, right? Yeah. That is on me. The textbook is correct. I don't know why I wrote that in my notes. Sorry. Okay, good. Right. So, back on track. These are all symmetries of the square as well, right? The powers of rho. Oh, so Thomas, is everything clear now? I wrote a wrong thing here. That's that blank space. Rho squared is not equal to sigma. Okay, good. Right, so, and are all even, something that we'll come back to, right? And what do we have? Rho sigma, rho squared sigma, rho cubed sigma, rho to the fourth sigma, i.e. sigma, all fix the square, and are odd. These 8 symmetries must all be distinct, right? Obviously, these all have to be distinct, or else we would have a smaller power of rho, b iota. Same rationale here. Okay. So, we've enumerated 8 distinct counting the things that fix this square in a different way. Okay? So, alternately, there are 4 possible points a symmetry can send V1 to. Right? I can keep it where it is, put it here, or put it here. Right? Additionally, for each possible image of V1 under some symmetry, there are 2 options for where V2 can go. Right? That is to say, an isometry has to keep these 2 next to each other. Right?
Exposed to adjacent vertices.
Right, right. An isometry sends adjacent vertices to adjacent vertices. Right? That's
Consequence of distance.
exactly. Okay, so that means that there are at most 8 distinct symmetries. Right? 4 times 2.
Given that there's no flexibility after you've assigned V2.
That's right. Yeah, if you pick 2 adjacent vertices,
There's no.
yeah, the rigidity of isometries forces your hand. Okay? So there are at most 8 symmetries of the square. So we listed 8 distinct symmetries, and that's the most that there can be.
That is them.
Right. So it turns out this implies that the symmetry group of the square is what we call D4, i.e. the set of these 8 symmetries. Or if we want to write this more compactly, it's just the group generated by rho and sigma. Okay. So, this is a valuable thing to write, but it doesn't exactly characterize the group as strongly as we might like. There's more that we can say about, i.e. our goal, or rather your goal tonight will be to write out the Cayley table for this group, okay? But I'm gonna give you some more tools to help you do that, okay? So I should also say, this is called the dihedral group. And so the subscript indicates the number of sides that the polygon has that it's the symmetry group of. Right? Yeah, that was confusing to me when I took algebra as an undergraduate. Wait, shouldn't it be D8? No, it's the subscript is indicative of the geometry, not the algebra. Okay, so notice that sigma rho to the k is a reflection through some line passing through the origin, right? Which implies that sigma rho to the k is an involution. So we have sigma rho to the k inverse. Well, how do we take the inverse of a product of things? We just take the inverse of each factor and reverse the order, right? Where, of course, here sigma inverse is just sigma, since it's a reflection. Or, equivalently, we can write this. Right? So, in summary, the equations and what we have here these equations allow us to write the Cayley table. Cayley table.
What does it mean involution has to do with the middle?
What does the fact that it's an involution?
Or the Toronto read it?
Yeah, right. So why did I say that it's an involution? Right. So I didn't write this. Yeah. Sorry. So yeah, you have this kind of a skew commutativity, right? It commutes in inverse, right? That's the point of it being an involution. Yeah, good. Okay. So this is what I want you to do for homework tonight. Now, of course, the table is in the book, but try to do it without looking at the book first, and then check your work. Okay. Okay, so I told you what the dihedral group D4 is. In fact, as you might expect, there's an entire family of dihedral groups for every positive integer n. Okay, yeah, and we'll talk about the small cases as we go. But, so let's have this general setup. So let's let n be a positive integer. Which is greater than 2. And suppose there is a regular n-gon centered at the origin with one of its vertices on the x-axis. Okay? Then the n-gon is fixed in much the similar fashion as what we just did by rho, the rotation through 360 divided by n, centered at the origin. And again, sigma h. Okay. Here's the general definition. The ahedral group Dn for n greater than 2 is the group of symmetries of the regular n-gon. And has generators rho and sigma. That is to say, of course, dn is just generated by rho and sigma. And dn has order 2n. Okay? Exactly analogous to the case for the square. Also analogous is that as you can immediately deduce, all the powers of rho are the even isometries, the even symmetries of dn. And anything with a factor of sigma is odd. Right? So that's worth writing down. I'll put that on the board. Even symmetries of the n-gon are rho squared up to rho to the n. And the odds are rho sigma, rho squared sigma, rho to the n sigma. Okay. So, what happens when n is 1 or 2?
N equals 1, you just get a point at the origin.
Right. So,
Equals 1 or 2.
so yeah. So
Rotations by 180 degrees.
it kind of breaks down. That's why we make this definition for dihedral group, right? There's meaning behind it, and we kind of lump them in the same. But to get this nice behavior that the symmetries of a regular n-gon have to be greater than 2. So let's look at the non-examples, the example non-examples. Non-examples. Okay. D1 is the symmetry group of an isosceles. Sorry, I never spelled this correctly. Isosceles triangle that is not equilateral. Right? D1 has order 2. There's just one reflection that fixes an isosceles triangle which is not equilateral.
So in this case, there is no row.
Exactly.
Same age.
Right.
If you orient it, so the
Right. Or the row is the identity. It's the identity rotation. Okay. Or rotation by 360 degrees, which is again the identity. Okay. Right. So how about the case of D2? D2 is the symmetry group of a rectangle that is not a square, which implies that D2 is equal to V4. Okay, so not all is lost when we have the case 1 or 2. It's just not as nice. It's not a regular polygon. Okay?
what definitions create those being the same group?
Just the generator definition.
Yeah, exactly. If you take rho to be your if you look back when we talked about the Klein-Ford group, you can choose any two to be generators, any two
Right.
elements. Okay, so that's a good homework exercise. Make explicit this.
So rectangles should be able to have a rotation by 180 degrees.
Yeah,
Just you can't turn it to 0 or 2, so that is the definition for D2. That makes sense.
Right,
Okay.
right.
And the other one can't.
so, what's that?
And the other one can't have a rotation by anything other than the identity, which makes it 360 over 1, which is a D1.
Yeah. Good. So, here, why don't we just say this, think about this tonight as well. Make this equality explicit. definition. For any positive integer n, the subgroup of even isometries, or I guess I can say symmetries here, of Dn is Cn, just the group generated by the rotation generator of Dn, which is something we've seen before, this cyclic group of order n.
So, oh, okay. So that's what it defines as a group?
Yeah, this is, I gave you an unrelated definition, a first principles definition earlier in the term, and now this is another way to define a cyclic group. And it's the subgroup of even symmetries, of even isometries for a given dihedral group, or one of these two cases, D1 or D2, also applies there. Okay. So, we've seen a shape before that has a cyclic group as its group of symmetries. And if you don't remember which shape I'm talking about, we'll get there shortly. Okay? But let me tell you this somewhat compelling theorem. For each positive n, there is a polygon having a symmetry group Dn and a polygon having symmetry group Cn. Okay, so this is by definition, right? That's how I defined the dihedral group for n greater than 2. It is the group of symmetries of a regular n-gon. And then, because I said positive n, I already told you for D2 and D1 what the polygons are. Okay? So let's talk about the polygons that have cyclic groups as their groups of symmetry. Okay? So, just case by case, let's start with C1. Can you tell me a polygon that has the cyclic group of order 1 as its group of symmetry?
Something very irregular.
Yeah, you can choose, on average, almost all shapes have this symmetry group. But there's a kind of nice answer.
Scaling triangle?
A scalene triangle, something that isn't even that odd, right? C1 is the symmetry group of a scalene triangle. Okay? What do we think of C2? Which, of course, iota, and the half turn about the order. It's kind of thematic, right? We can think of a pretty simple shape that just isn't exactly as nicely behaved as we might like.
If you made a cubic function to a polygon.
Okay, that's an interesting idea.
That shape would do that.
Yeah, I think you're right. Here's something that is kind of maybe simpler.
Parallelogram?
A parallelogram that isn't a rhombus. Okay? A is the symmetry group of a parallelogram that is not a rhombus.
You can't be rectangle, I think.
No, but a rectangle is a rhombus, right? It has
No.
No, you're right. Yeah, not a rhombus nor a rectangle. Good. Okay, how about Cn? The arbitrary cyclic group of order n. How can I construct a polygon? This is the shape I was referring to that we looked at before when we first talked about symmetries of shapes in the plane. Cn takes a bit of work. For example, I'm going to draw you this picture. Okay, let's say for n equal to 3, let's just take an equilateral triangle.
And then you can get rid of this line symmetry.
I'll put an equilateral triangle inside, and then, let me make sure I can do this correctly. Bisect each half.
No, it can't be reflected.
Right, this shaded figure has no reflections. It only has a rotation by 120 degrees as its only symmetry.
Do you need to do the shading, or could you just take the whole figure?
No, I just did the shading to make it more clear what shape I'm looking at.
Just one line, it was just, yeah.
Yeah. But I had to do it to be able to draw it. I had to like insert those lines just to make it nice looking. So the shaded figure has no reflections as symmetries. Only rho only rotation by 120 degrees about the center of that shape as a symmetry. Okay?
We have more problem for n equals 5, right?
Is that right?
Back when we, earlier,
Like, what chapter was that from?
I remember having to draw a figure.
depending on the connected alternating vertices.
That might have been on a practice exam, right?
Oh, maybe.
Yeah, I think that was on a practice exam. Right, yeah, you were asked to draw, in the practice exam, you were asked to draw a figure that only had, rotation by 180 degrees as its symmetry, right?
By
Maybe,
20 degrees, I think. No, it would have been triangle. Yeah, it was supposed to be 5.
yeah, I forget the exact wording of the problem, but yes, there was a similar, type of question. Now, there's also, at the bottom of page 59, there's a, the case of C6 is drawn, which you might want to take a look at. It's the same type of construction where you like embed a shape inside a regular hexagon in that case. Okay, so I'll just write that down. Also see page 59 of text for n equals 6. Okay, so obviously, notice I didn't write a proof for this theorem, just because I don't have any like systematic formal way that to develop Cn. But you can kind of see what the right thing to do is. Okay, especially if you look at some more examples. But I'm not going to try to draw a hexagon. Okay? So, the amazing thing, which we will hopefully get to tomorrow, is that the converse of this theorem is also true. That every polygon has symmetry group Dn or Cn for some n. Okay? And that's due to Leonardo da Vinci. So, before we begin on chapter 8, let me just mention a few problems you might try for homework. Let's just say 7-4, 7-5, 7-7, 7-13, and 7-16. Okay. So that'll do it for chapter 7. Now, we want to move on to further refine our classification of isometries. Okay? And truth be told, we're almost there. There's only just one case left of something that we haven't addressed explicitly. And these isometries are called line reflections. Right, so just to be a little more explicit in what I was just saying, we've classified all even isometries as either translations or rotations. Okay? And then furthermore, there are essentially two types of odd isometries, right? There are single reflections and products of 3 reflections. Okay? So the case we have to address now is this case of products of 3 reflections. We want to address / investigate products of 3 reflections. And as such, let's start with a special case. Let's assume first that lines A, I guess I should say lines A and B are both perpendicular to line C. Okay? Then, clearly, as we've discussed at some length by this point, sigma B, sigma A is a translation or glide and sigma C is a reflection. Definition. Glide reflection, right? Sigma C, sigma B, sigma A is called a glide reflection. Why the use of the terminology glide? I'm not sure, but it is nicer to say than translation reflection. It's fewer syllables. Okay, so yeah, so this is, I think, I'm just gonna state this theorem. It's a lot. And then I think we'll just call it a day. Okay. So, a glide reflection fixes no points. That makes a ton of sense, right? A translation doesn't fix any points. So, furthermore, it fixes exactly one line. Its axis. Sorry, I didn't give you a full definition here. This is called a glide reflection with axis C. Okay? Furthermore, the midpoint of any point and its image under a glide reflection lies on the axis of the glide reflection. kind of see, just at a glance, most of these things make sense, right? From what we know about translations and reflections. But yeah, we'll start off tomorrow by giving a rigorous treatment of this. Okay, and then, yeah, just an update. I think the exam will only cover up through section 8.1. We're not gonna have anything on the test on Thursday from section 8.2. We probably will start 8.2 tomorrow, but just be concerned with up through section 8.1.
Is this the only case we're addressing with three reflections?
I'm sorry.
We're addressing other cases of three reflections?
Yeah, so we'll see that this actually covers a lot of